Day 10. Okay, this is a special case factoring where you have the difference of two squares. This is 5x squared and this is 2 squared, and you have the difference. So whenever you have the difference of two squares, you're always going to have the product of two conjugate pairs, excuse me. So the first item you put here, the second item you put here, those are those items, and then you just put the opposite signs in between them. Oops, I forgot the X in them. This will always work. It's always going to be the product of two conjugate pairs, because when you FOIL this, your first is 25x squared, your outer is negative 10x, your inner is a positive 10x, and your last is negative 4. These will always add up to 0 and go away, and you'll always have the first item squared minus the second item squared. Okay, remember the first step in any factoring problem is to take out a GCF if there is one, and then so we have a 2. And this becomes 9a squared minus 49b squared. And hopefully you recognize these items as being perfect squares, and this is the difference of two squares. So we have the conjugate pairs. So we're going to say 2 times the first square root is 3a, and the second one is 7b. And then we just put our opposite signs in between them. And you can FOIL to make sure it works out, but that's going to work out. Okay, remember the first step in any factoring problem is to take out a GCF if there is one. So that'll be a 4, so this will be a 16m to the 4th minus y to the 4th. And we have the difference of two squares. This item is 4m squared minus this item is y squared squared. So we have the difference of two squares. So we're going to have conjugate pairs. This will be 4m squared, okay, remember the first step in any factoring problem is to take out a GCF. So we'll factor out the 4. This will become 16m to the 4th minus 4y to minus y to the 4th. Let me erase that. Oops. Okay, the first step in any factoring problem is to take out the GCF, which is a 4, and that's going to leave us with 16m to the 4th minus y to the 4th. Okay, and hopefully you recognize this as the difference of two squares. Now the square root of this is 4m squared, and this is y squared, So that's the difference of two squares, and that's going to become the product of two conjugate squares. This first item will be 4m squared, and the second item will be y squared, and we'll put the opposite signs in between them. And don't forget about this 4. Okay, this can no longer be factored, but this is the difference of two squares. The first, in other words, this is 2m squared minus y squared. So that portion is going to become 2m plus y times 2m minus y. That's how this will factor. And then we still have this, so we'll put that in front. 4m squared plus y squared, and we still have this, 4. So that entire thing factors like that. Again, we have the difference of two squares. This is already shown as a square, but we can write this as minus 9 squared. So you have this first item squared minus 9 squared, and you're going to have the conjugate pairs. The first item is y plus z. The second item is 9. and we put a plus for one of them and a minus for the other to give us our conjugate pairs, and nothing can be simplified, so we're done. Again, we have the difference of two squares. This is 4 squared. This is already written as a square. So, our conjugate pairs, we're going to have 4 first, and then the second item is going to be x plus 3y. So we'll have a plus in the first spot and a minus in the second spot. Be careful because this negative is going to distribute here. When we get rid of these parentheses, they just disappear. So we have 4 plus x plus 3y. But over here we have 4 minus x minus 3y. Now you may have skipped this step and gone right from here to here, but just be careful to understand that that negative is going to distribute when you're doing the minus portion of it. Okay, again, we have the difference of two squares. The first item is p squared squared minus 16 squared. So you're going to end up with the conjugate pairs. The first item's p squared. The second item's 16. You put a plus in one spot and a minus in the other spot to give you your conjugate pairs. Now this is prime because it's the sum of two perfect squares. But this here is the difference of two squares. And this is going to be the first item and the second item, right? But this we just write down again because that portion cannot be factored. So this is our final answer. If you stopped here, that is factored, but it's not completely factored. So that would never be your final answer. If you can continue to factor anything, you have to do that until you can no longer factor anything. Okay, this is another special case. You hopefully will recognize a perfect square. If the outer terms are perfect squares, you might have a perfect square. Okay, so what you do is you put this first, you put this second, the square root of those items, right? And you put this sign third. This may not be the answer. In order for this to be your answer, you have to double check the middle term. The middle term has to be twice the product of these. So the product of these two is negative 3k. Twice that really is negative 6k. So this works. Okay, here we have two things in one. If you notice, this portion here is probably a perfect square because we have a perfect square here and a perfect square here. So let's test that. The square root of the first item is 4m. The square root of the last item is 1. And we'll put this sign here. Does the product of those two things, twice the product of them, equal the 8m? And it does. So this is a perfect square. And now we have the difference of another square. So when you have the difference of two squares, you're always going to have conjugate pairs. Your first item is 4m minus 1. And your second item is n. And you put a plus in one and a minus in the other to make your conjugate pairs. And nothing can be simplified, so that's done. Okay, the previous problem I did was actually number 23. So I did number 23 on accident, last problem, so now I'm going to do number 21. All right, number 21, again, hopefully you recognize this as a perfect square. That's a perfect square, and this is a perfect square. When you have that, it's very likely that you have a perfect square. So we'll double check it. The square root of the first item goes here. The square root of the last item goes there. This sign goes there. This will be the answer if twice the product of these two terms times 2, or twice the product of those two terms is equal to that. And it is. So that's the answer. Okay, we have 4 terms, but if you notice, these 3 terms are a perfect square. This is going to be a 2r and a 3. The square root of this is 2r. The square root of this is 3. We'll put a minus in between them and double check the middle term. 2r times negative 3 is negative 6r, and when we double that, we do get negative 12r, so that works. Minus s squared. So we have the product, the difference of two squares. So we're going to have the conjugate pairs. You always put the first item first. The second item goes here. And in order to have conjugate pairs, you put a plus in front of one and a minus in front of the other. And then you'd combine like terms if you could, but you can't, so you're done. Okay, in this problem, I got to do a little grouping in order to get my two squares. So these terms I'm going to group together as one item. So I'll do this. X squared minus, and I'm going to put parentheses. And the parentheses now are going to cause each of these to flip. So that's going to become a y squared minus 2y plus 1. So that I can treat this all as one group. And this is a perfect square. The square root of the first item goes first, the square root of the last item goes last, and the sign in between them goes there. Twice the product of those two things really is my middle term, so this works. So I have the difference of two squares, which is going to give me conjugate pairs. I put my x here, and I'm going to have plus this y minus 1, and I'm going to have x minus that y minus 1, and I'm going to clean this up so that I have in the first parentheses x plus y minus 1, and then I'm going to distribute this negative and get x minus y plus 1, and that's the final answer. All right, remember the first step in any factoring problem is to take out a GCF. So everything's divisible by 2, so let's do that. And now it looks like we have a perfect square because the outer terms are perfect squares. So let's put the square roots of those two items. This is 7m, right? This square root is 3n. The sign is a plus. Is the middle term here equal to twice the product of these two terms? Yeah, well, 7m times 3n is 21mn, and twice that really is that. So that is the answer. So that's my final answer. In a problem like this, you can substitute. Do something like x is equal to p plus q. And then you can rewrite this as 2x squared, well, not 2x squared, just x squared plus 2x plus 1. And this is a perfect square. You put your square root of the first item, the square root of the second item, this sign in between them. Double check your middle term, but it works. But remember, you really don't have an x. X is p plus q. So you're going to have, you substitute your x back and you have p plus q plus 1, squared. What am I doing? And that's your final answer. Okay, again, substitute. Do something like x is equal to a minus b. And then you're going to have x squared plus 8x plus 16. And again, this looks like a perfect square. The square root of the first item goes there. The square root of the second item goes there. That sign goes in between. Double check the middle term, see that it works, and it does. So now you got to resubstitute a minus b for x. So this is going to be a minus b plus 4 quantity squared. And now you're done. Okay, here we have the difference of two cubes. So there's a formula. If you had a cubed plus b cubed, the way you do this is you make a binomial and you make a trinomial, okay? And the binomial, these items, the a and the b, go there. And in the trinomial, just remember square, product, square. square, product, square. So you put the square of the first thing, the product of the two things, and then the square of the last thing, okay? And finally, just remember the acronym SOAP. Same, opposite, always positive. So same, you put the same sign in between. Opposite, you put the opposite of that sign, and then always positive. So the sum of two squares will factor like this. If you had the difference of two squares, you still do the binomial times a trinomial, and you still put these cube root items there, and then you go square, product, square. And when you apply SOAP, this time this is a minus, so same is a minus. Opposite of that minus, and then always positive. So this is the difference of two cubes. Okay, so in this problem down here, you have to recognize what the cubes are. This is y cubed minus 4 cubed. So we're simply going to make a binomial times a trinomial. We'll put the cube root items here, so y and 4 go here, and then we'll go square, product, square. And then we'll use the acronym SOAP. So the same, opposite, always positive. And there's our answer. So there's a little formula you have to remember for the sum or the difference of two cubes, and then you can just apply that method. Okay, in a problem like this, you may not realize that 343, the cube root of that is 7, but you probably are tipped off that you need to do a cube root because this is a cube. So we probably have the sum of two cubes here. So just go in your calculator and cube root 343, and you'll see that it's 7. So now you know that you have r cubed plus 7 cubed. And remember, you always make a binomial times a trinomial. The cube root items go in the binomial. And in this, we put square, product, square. So we square that, the product of the two items, and the square of the last item. And then remember, we use SOAP. Same, the same as this, opposite of that, and always positive. So this is the final factored answer. Okay, again, with those cubes, it's pretty obvious we have the difference of two cubes. 8, the cube root of 8 is 2, so this is 2x cubed minus y cubed. So remember, make your binomial and your trinomial. The cube root items go here, and then we're going to do square, product, square. The square of the first item is this, the product of the two items is this, and the square of the last item is there. And then we're going to apply SOAP. Same minus opposite, always positive. Okay, here we have the sum. We obviously have cubes. You just need to find what the cube root of 64 is, and that's 4. So this is 4g quantity cubed, plus the cube root of 27 is 3. So we have 3h quantity cubed. Now that we know what the cube root items are, we know we have a binomial times a trinomial. The cube root items go in the binomial, and then we go square, product, square. So square is 16g squared. The product of those two items is 12gh, and the square of the last item is 9h squared. And then we'll apply SOAP. So we have same, that's the same, opposite of that, and always positive. And we're done. Okay, page 411. Okay, on this section, there's nothing new. Everything is a review. The difficulty here is that all the different types of problems you have learned are scrambled, and you have to recognize what you're doing in order to factor. Anyway, here we have the difference of two squares. So the conjugate pairs would be 10a plus 3b times 10a minus 3b. Whenever you see the difference of two squares, it's always conjugate pairs. All right, in a problem like this, the first thing I would do is reorder it. So I'm going to put it in descending order. And then remember, if you have a GCF, always pull out the GCF first. So everything is divisible by 6 and by at least a p cubed. That leaves behind a 2p cubed plus 3p squared minus 4. I was thinking that we may be able to factor after this, but because we go from a cube to a square down and no p down to 4, this is going to be our final answer. We're not going to be able to factor that last thing. All right, here we have a trinomial with no leading coefficient, so that's easy enough. We'll just go to x and x. We're looking for factors of 35 that give us a sum of 2, so that's a positive 7 and a negative 5, and we're done. This problem is trying to trick you. If this were a minus here, this would be the difference of two squares. But this is a sum, and we, unless there's a GCF in this, we wouldn't be able to factor at all, and there is no GCF. So this is just a prime. Okay, remember the fastest way to factor a trinomial is not using these tricks. But if you get stuck and you need a little device to help you, you can use the California method. So 6 times negative 3 is negative 18. So I'm looking for factors of negative 18 that give me a sum of negative 17. And it's pretty obvious. That's got to be a negative 18 and a positive 1. So when I do this, I take my 6b and I put it over negative 18 and over a positive 1. I can reduce the first fraction as dividing by 6, so I have a b over negative 3. And then remember, all you do is you pop this up and you pop this up, so I'm going to have b minus 3 times 6b plus 1. I think it would have been faster to just go right from there to there, but there's a little trick to help you if you get stuck. All right, in this problem, there's something common to each term. Each term is at least divisible by 3. They have at least an m, and they all have at least an n. So that's the GCF that I'm going to start with. And I'm going to have a 6m squared left from the first term plus mn from the second term minus 2n squared from the last term. Okay, and again, I think it's easiest just to do this straight factoring, but if you need some help, you can do the California method. 6 times negative 2 is negative 12, so we're looking for factors of negative 12 that give us a sum of 1. So that's going to be a positive 4 and a negative 3. That gives us a sum of 1. Okay, so we're going to take our 6m. Because of the n squared, we'll take half of those variables and put them on the bottom. So I'll put positive, these are two factors that I'm after. So 4n on the bottom of this one, and 6m, and negative 3n on the bottom of this. I reduce this fraction to be 3m over 2n. I reduce this fraction to be a 2m over a negative n, and then I just pop this up and pop this up so that I end up with 3m plus 2n times 2m minus n, and don't forget about this that we factored out in the beginning. It's a common mistake to write down that your final answer without that item that you factored, so just remember that, and that's our answer. All right, in a problem like this, I'm not going to bother to use any special devices because I don't have any choices. My first position has to be 2p and p. There's no other way to get to 2p squared. My outer two items, or my last items, have to either be 15 and 1 or 5 and 3. That's the only way to get to 15. So let's look at the 5 and 3. If I put my 5 here and my 3 here, oops, I can't forget my Q, I'm going to have 5 on the inside and 6 on the outside. Here's my inside and here's my outside. And those will add up to my 11. So now we're done. All right, here, notice that this is a perfect square and this is a perfect square. So I think this is probably a perfect square. I'll put the square root of the first item here and the square root of the second item here. I'll put this sign in between them, but then I'm going to double check my middle term. Twice the product of these two things. So twice the product is 14 kr, twice that is 28 kr, so this is the answer. Okay, here we have 4 terms, none of them are squares, so I'm going to factor by grouping. I'll take these first 2 and group them together, and I'll pull out an m. Oops, not an m, an n. I'll pull out an n, and I'll be left with m minus 2. Remember, the easiest way to do this is leave a big space and put m minus 2 down again, because you know you have to leave that behind, and then think about what you had to factor out to do that. So it's got to be a positive 5. And now we have 2 terms. The m minus 2 is common to both of them, so you factor that out, and you're left with n plus 5. And that's the final answer. You can, if you're not confident, FOIL this and make sure you get back to the original. Okay, here I have 4 terms. I'm going to factor by grouping again. When I group these 2 together, I can see that an x squared can come out of both of them. It leaves behind an x in the first term and a positive 3 in the second. So I'm going to leave a big space and I'm going to put down an x plus 3 again, because what you leave behind here has to be identical there. Then when I look at these, I can see that a negative 9 has to go here, so that when I multiply, I get back to those. Now the way this is written, I have 2 terms. Here's a term, here's a term. My x plus 3 is common to each of those terms. It leaves behind an x squared from the first one and a minus 9 from the second one. Now, I can't stop here, because although the first item is prime, this here is the difference of 2 squares, and that's going to factor as conjugate pairs. X plus 3 and x minus 3. And then I have this x plus 3 here. Well, if you really, you could circle this answer, but if you really want to write this nicely, you would write x plus 3 quantity squared, because there's 2 of them, times x minus 3. And that would be your final answer. Okay, this problem is trying to trick you into thinking this is a difference of 2 squares, because this is a perfect square and this is a perfect square. But this is the sum, it's not the difference. So we're not going to be able to factor this. So this is simply prime. Okay, in a problem like this, I'm not going to use some special gimmicky California method. I'm just going to go right to binomial times a binomial. I'm not sure right now about this position, but I know this has to be a 1, because those are the only 2 factors of 1. So now I'm trying to get my outer and inner terms to add up to a negative 1. Well, I've got to have a 3k and a 2k. My outer will give me 3, my inner will give me 1 or 2, and that will give me a sum of 1. So if I put the negative here, that's going to be a negative 3k on the outside, a positive here, that'll give me a positive 2k on the inside. That adds up to my negative 1. All right, in this problem we have the difference of 2 squares. First, identify what those are. This is x squared, and this is 25 squared. So we're going to have conjugate pairs. We put the first item here, the second item here, and then we put the opposite signs. Well, this is the sum of 2 squares, but this is the difference of 2 squares, and this last one can continue to be factored as the difference of 2 squares. So we put the square root of the first item first, the square root of the second item second, and then plus minus. And of course, we still have this. So that's the final answer. Okay, here we have 4 terms, so I'm going to group these two grouped together. There's a b in common. So I pull out the b, and I'm left with a plus 6. So if this is going to work, I have to leave behind another a plus 6 for these two. And if you look, it's a common c. So if you take out a positive c, it really does multiply back to this. So here we have 2 terms. The a plus 6 is the common factor in each term, and then it leaves behind the b plus c. If you're not sure about it, FOIL this and make sure you get back to the original. All right, remember the GCF is always your first step. They're both divisible by 4 and by y, so that leaves behind a y minus 2, and that's all you can do. Okay, again, the fastest way is just to factor this without a device, but if you need help and you get stuck, you can always multiply the two things together, the two outer things, to get negative 28. So I'm looking for factors of negative 28 that give me a sum of negative 3. So negative 7 and positive 4. That will do it. So I'll take my 14z squared, or just z, and I'll put it over negative 7, and I'll do that again over positive 4. These reduce. The first one becomes 2z over negative 1. The second one becomes 7z over positive 2. And I just pop these up. So my final answer will be 2z minus 1, 7z plus 2. Remember, the first step in any factoring problem is to take out the GCF. Now you can start factoring each one, but 16 is common to both of them. So if you take out this 16, you'll be left with 16b squared minus 25c squared. And this is the difference of two squares. The square root of 16 is 4, so this is 4b in the first spot. The square root of 25 is 5, so that's 5c in the second spot. To make these conjugate pairs, you put a plus and a minus. And don't forget about the 16 that we factored out originally. When you see a problem like this, what you should be thinking about is the fact that there's a cube here and that there's two terms. So I know I have the sum of two cubes. So figure out what those cube roots are. 10z cubed is 1,000 cubed, and 8 cubed is, Remember, the first step in any factoring problem is to take out a GCF. Both of these items are divisible by 8. So let's start there. 8, and we'll have 125z cubed plus 64. Now, I can see that this is the sum of two cubes. The cube root of this is 5z. The cube root of 64 is 4. So remember, when you have the sum of two cubes, you're always going to end up with a binomial times a trinomial. In the binomial, you put the cube root items. In the trinomial, you go square, the square of the first thing, product, the product of those two things, and then square, the square of the last thing. And then we'll use SOAP. Same, that's a plus, so same, opposite, always positive. And just don't forget the 8 that we factored out originally. So that's the final answer. Okay, again, I probably wouldn't use any devices for this. I'll show you both ways. If you just factor this, my inner and outer are trying to get me to 23. So if I had 5r here and 2r here, okay, and if I put 5s here and 1s here, my outer is going to give me 25, My inner is 2, and the difference there is 23. So this must be a plus to give me a positive 25, and this must be a minus to give me a negative 2RS, and that'll give me my difference of 23. So there, I'm done. If you couldn't see that and you needed a little device to help you with that, you multiply your outer two things together to get negative 50. I'm looking for factors of negative 50 that add up to 23. So negative 25 and positive 2. And then you take your 10R and you put it over your negative 25 and your 10R and put it over your positive 2. Let me include the S down here. When you reduce the first one by 5, you'll get 2R over negative 5S. And when you reduce the second one by 2, you get 5R over a positive S. You pop this up and get this factor, and you pop this up to get that factor, and you're done. All right, in this problem, I can see that there's an 8 common to every one of those numbers, and we have at least an x squared in each of those terms. So we'll factor that GCF out. That's going to give us a 4 for the first term, a positive 2x for the second, and a minus 3x cubed. This won't be factorable because our variables skip, so we're done. You can factor this using just traditional factoring methods, or you can try to use the California method. The problem with the California method is 14 times 25 is such a large number. So I'm a little resistant to trying that. And so instead, I'm going to jump right to this. I'm just going to start by guessing that this is going to be 7x and 2x. I could be wrong. It could be 14 and 1. All right. And then I'm going to start by guessing that the 25 is going to be 5 and 5. I could be wrong. It could be 25 and 1, but I doubt it. So I'm going to put 5 and 5. And then I'll think about the signs to get me there. Well, I'm trying to get to a negative 25. So if I put a negative here, that'll get me negative 35 on the outside. So a positive here gets me to a positive 10 on the inside. And that really does add up to my negative 25 in the center. All right, this is a nice problem because it's trinomial with no leading coefficient, so I can jump right to y and y. I'm looking for factors of 10 that give me a difference of 3, so positive 5 and negative 2, and we're done. Okay, remember in any factoring problem, you always take a GCF out first, so I'll take a 2 and an a out. That's always your first step. That leaves behind an a squared plus 3a minus 2. And this does not have a leading coefficient, so I can go right to a and a. I'm looking for factors of 2 that add up to 3. So that's actually, there are no factors of 2 that add up to 3. So that cannot be factored further. So that'll be that. Okay, this is a rough problem because 18 has so many possible factor choices. So I'm just going to take a look at the California method. If I take 18 and multiply by negative 35, I get to negative 630. And actually, now I think I'm done because I can see that my factors I'm trying to add to 53 are going to be positive 63 and a negative 10. And that's just, this was divisible by 10. I kind of lucked out on this problem, but those are the two factors that I'm after. So, oops. All right, so I'm going to get 18p, and I'll put it over a positive 63. I'll put one of those r's down below. And I'll have 18p over my negative 10, and I'll put one of my r's down below. I'll simplify each fraction. This is divisible by 9, so I'll have 2p over a positive 7r. and this one's divisible by 2, so I'll have 9p over negative 5r. Pop this up, and I'll have 2p plus 7r. Pop this up, and I have 9p minus 5r, and I'm done. Now, in a lot of problems, when your product is so large like this, it's very difficult to find the factors that you're after to do this. But in this case, it really was pretty simple. Okay, here we have the difference of two squares. So I can rewrite this if you want as the first item squared minus the second item squared. Remember, you always have conjugate pairs. You always put the first item down first, and then the second item down second. And to make them conjugate pairs, you put a plus on one and a minus on the other. Then you simplify if you can, but in this case you can't, so we're done. Okay, in a problem like this, I'm going to substitute. I'll say a variable, any variable I want, like x is equal to 5r plus 2s. And that gives me x squared minus 6x plus 9. And I recognize this as being a perfect square. You put the square root of the first item there, the square root of that there, this sign here, double check the middle term, and it works. So now I've got to resubstitute this for x. So I'm going to end up with 5r plus 2s minus 3 quantity squared. And I can't simplify any further. So I'm done. Okay, here we have a z to the fourth. So in my first position, I'm going to have z squared because that'll multiply out to my z to the fourth. And now I'm looking for factors of 20 that add up to negative 9. So negative 5 and negative 4. Well, this is prime and it cannot be factored. But this is the difference of two squares. So you're going to have conjugate pairs. The first item goes first, the square root of the second item goes second, and to make it conjugate pairs, we put a plus on one and a minus on the other, and then don't forget about that. So that's the final answer.